Now we turn to traversals. A traversal is a way to visit every node in the tree, one by one. We will meet 4 of them and see how they differ. Every traversal here visits all n nodes exactly once. They only differ in when they visit the root compared to its 2 subtrees. A tree with 1,000 nodes is 1,000 visits in every order. The order changes the sequence, but never the amount of work, so all of them are big, O of n. Preorder visits the root before either subtree. You handle the root first, then go down. Inorder visits the root between the 2 subtrees. You do all of the left side, then the root, then all of the right side. Postorder visits the root after both subtrees. You finish both children first, and the root comes last. Level order is different. This course does it iteratively, with a queue, not by recursion. It visits one level at a time from the top down, left to right. Preorder visits the root, then the left subtree, then the right subtree. The rule is simple. We output a node the moment we reach it on the way down. So we start at the root 50 and output it right away. 50 turns amber and 50 joins the output strip below. Now we go into the left subtree. We reach 61 and output it at once. 61 turns amber and 50 behind us turns green, which means already visited. We keep going left and reach 77. We output 77. It is a leaf, so there is nothing more on its left or right. We go back up to 61 and take its right child 8. We output 8. That finishes the whole left side of the root. Now we go into the root's right subtree and reach 12. We output 12. 12 has a right child 99. We reach it and output 99. Last 99 has a left child 5. We output 5. The full preorder is 50, 61, 77, 8, 12, 99, 5. Root first, then the whole left side, then the whole right side. This is preorder as clean recursive pseudocode with no language details. If x is not nil, first visit x, then walk the left child. Then walk the right child. Nil just means an empty tree, so an empty subtree does nothing at all. That is the whole algorithm in 4 lines. Now the same thing in C, the function is preorder, and it takes a pointer x to a node. First the base case. If x is equal to null, there is nothing here. So we return and do nothing. Notice the pseudocode wrote this as if x is not nil, and the C writes it inverted as an early return. Same rule. Then we print x arrow data. That is the visit, and in preorder it happens first before either child. Then we call preorder on x arrow left, the left child. And then on x arrow right. Only the position of that print line changes between the 3 orders. Everything else stays the same. Inorder visits the left subtree, then the root, then the right subtree. Watch it go all the way down the left before it visits anything. We begin at the root 50. This is just an encounter. We arrive, but we do not output 50 yet. The output strip stays empty. We go left first. We move down to 61. Again, this is only an encounter. We do not output it yet. We keep going left, looking for the leftmost node. We reach 77. It has no left child, so there is nothing more to the left. Now we have a real visit. We output 77 and it appears in the strip. This is the first token. 77 is done, so we return to its parent 61. Its left side is finished, so now we visit 61. We output 61. After the root 61, we go into its right child 8. 8 is a leaf, so we visit it right away. We output 8. The whole left subtree of 50 is now done. So we return to the root and visit 50. We output 50. See how we did not output 50 until its entire left side was finished. Now we go into 50's right subtree and reach 12. 12 has no left child, so we visit 12 and output it. 12's right child is 99, but 99 has a left child, 5. So this is just an encounter. We go left first, and we do not output 99 yet. We reach 5, the leaf. We visit 5 and output it. Finally, we return and visit 99 last. The full Inorder order is 77, 61, 8, 50, 12, 5, 99. People often think Inorder always gives sorted output. That is not true for a general binary tree. This little tree is a valid binary tree with a correct shape. Its root is 40. We begin at 40 and go left. This is only an encounter, so we do not output it yet. We descend left to 90. Again, just an encounter. We keep going left. We reach 70, a leaf. Now a real visit. We output 70. It is the first token. We return to 90 and visit it. We output 90. Then we take 90's right child, 20, a leaf, and visit it. We output 20. The left subtree of 40 is done, so we return and visit the root, 40. We output 40. Last, we take 40's right child, 10, and visit it. The full Inorder sequence is 70, 90, 20, 40, 10. That is clearly not sorted. So here is the rule to remember. Inorder gives sorted output only for a binary search tree, which we meet in Chapter 10. It never sorts a general binary tree. The traversal order comes from the shape of the tree. Sorted output is an extra promise, and only a search tree makes it. This is the main anchor for the chapter. One idea shown at 3 levels of precision, side by side. The first step is fully explore the left subtree. In pseudocode, that is Inorder tree walk on X's left. In C, it is Inorder of X arrow left. The second step is visit the root itself. In pseudocode, that is the word visit applied to X. In C, it is print X arrow data. The third step is fully explore the right subtree. In pseudocode, that is Inorder tree walk on X's right. In C, it is Inorder of X arrow right. The last row is the stopping rule. Stop at an empty subtree. In pseudocode, that is if X is not nil. In C, it is if X is equal to null, return. Nil and null mean the same thing here, the empty tree. Here is that same walk as a full C function. It is called Inorder, and it takes a pointer X. Notice one thing about the order. The base case sat last in the table, but in the code it is checked first. If X is equal to null, we stop. Then we go left, all the way down. Then we print the value. That is the visit, and it sits between the 2 subtrees. That is what Inorder means. And then we go right, left root right. This is a quick check for you. Look at the small tree with 5 nodes. Your job is to find its Inorder sequence. Take a moment and try it yourself before I show the answer. Remember the rule for Inorder. You visit the left subtree first, then the node, then the right subtree. Start at the root, 20, and go into its left subtree, rooted at 35. Inside 35, go left first to 9, which is a leaf, so you visit 9. Then you visit 35. Then its right child, 41. Then come back up and visit the root 20, and last its right child, 3. Pause and check your answer. Here is the answer. The Inorder sequence is 9, 35, 41, 23. The whole left side of 35 comes out first, then 20, then 3. Postorder visits the left subtree, then the right subtree, then the root. So a node is output only on the way back up, after both its children are done. We begin at the root 50 and go left. This is just an encounter, so we do not output 50 yet. We descend to 61. Again just an encounter, we keep going left. We reach 77, a leaf. Both its children are empty, so it is done. We output 77, it is the first token. We go back to 61 and take its right child 8, a leaf. We output 8. Now both children of 61 are done, so on the way back up we output 61. We move to the root's right side and reach 12, just an encounter. We do not output it yet. We go down to 99, still an encounter. It has a left child 5, so we go there first. We reach 5, a leaf. We output 5. Now 99's children are done, so we output 99. 12's children are done, so we output 12. Finally, the root 50 is done last of all. We output 50. The full post order is 77, 8, 61, 5, 99, 12, 50. Notice what that trace showed. The root always comes last in post order, and that is not just a curiosity. This order is exactly how you safely free a whole tree. You free each child before its parent, so no pointer is ever read after its node is gone. The pseudocode shows the pattern clearly. If x is not nil, first walk the left subtree, then walk the right subtree, and only then visit x. The visit comes last. Compare it with preorder, the same 3 lines in a different order. In C, the function is postorder, and it takes a pointer x to a node. First, the base case. If x is equal to null, just return. An empty subtree has nothing to do. Then we call postorder on x arrow left, the left child. Then postorder on x arrow right, the right child. Only now do we visit the node and print x arrow data. That is why the root prints last. And here is the pattern across all 3 orders. Only the position of the visit line moves. The recursive skeleton, the null check, recurse left, recurse right, never changes. The 3 orders we saw are depth first. They go all the way down to the bottom before backing up. Level order is different. It visits the tree top to bottom and left to right inside each level. For this, we need a queue from Chapter 7, not recursion. First, enqueue the root. Then repeat these steps. Dequeue a node, visit it, and enqueue its children that are not null. Stop when the queue is empty. Now let's trace level order with a real queue. The tree on the left shows 1 node process per step. The table on the right adds 1 row per step and keeps every earlier row. We start by enqueuing the root 50. The queue holds just 50. Step 1. We dequeue 50 and visit it so 50 turns green and joins the output. Then we enqueue its 2 children, 61 and 12. The queue now holds 61 and 12. Step 2. We dequeue 61 and visit it. Then we enqueue its children, 77 and 8. The queue now holds 12, 77, and 8. Step 3. We dequeue 12 and visit it. 12 has only 1 child, 99, so we enqueue just 99. The queue now holds 77, 8, and 99. Step 4. We dequeue 77 and visit it. It is a leaf, so there is nothing to enqueue. The queue holds 8 and 99. Step 5. We dequeue 8 and visit it. Also a leaf, nothing to enqueue. The queue holds just 99. Step 6. We dequeue 99 and visit it. It has a left child 5, so we enqueue 5. The queue holds just 5. Step 7. We dequeue 5 and visit it. It is a leaf, so nothing is enqueued and the queue is now empty. We are done. That was 7 dequeues in all, 1 per node. The visiting order is 50, 61, 12, 77, 8, 99, 5. It comes out level by level because the queue never holds more than 1 level at a time. Let us line up the visiting order, 1 token per dequeue. First out is the root, 50. That is level 0 on its own. Then 61, the root's left child. Then 12, the root's right child. Those two are all of level 1 left to right. Then 77. Then 8, those two are 61's children. Then 99, 12's only child. That finishes level 2. And last 5 alone on level 3. Read the strip and you can see the levels. 1 node, then 2, then 3, then 1. Top level first and left to right inside each level. The pseudocode is short. If the root is nil, return. Otherwise make an empty queue and enqueue the root. Then, while the queue is not empty, dequeue a node, visit it, and enqueue each child that is not nil. Notice there is no recursion here at all. The queue does the work the call stack did in the other 3 traversals. In C, the function is level order, and it takes the root pointer. If root is equal to null, we return right away. An empty tree prints nothing. We make an array queue that holds node pointers. This array is our queue. Front, count, and rear all start at 0. These 3 indices run the circular queue. We put the root into the queue. We store it at rear, move rear forward with a mod, and add 1 to count. The loop runs while count is greater than 0, that is, while the queue is not empty. We read the node at the front of the queue into X. Then we move front forward with a mod and take 1 off count. That is the dequeue. And we visit the node by printing X arrow data. The enqueuing of the children is on the next slide. Still inside the loop, if X has a left child that is not null, we enqueue it. We store it at rear, move rear forward with a mod, and add 1 to count. If X also has a right child, we enqueue that 1 in exactly the same way. Then the loop goes round again and dequeues the next waiting node. One thing to notice, this queue is exactly Chapter 7's circular array queue. The only change is that it holds node pointers instead of integers. Nothing new is invented here. There is one precondition on that fixed array, and it is easy to get wrong. QCAP must hold the most nodes that ever wait at once, and that peak is not the widest level. While the queue drains level I, it is already filling with level I plus 1, so it holds parts of 2 levels at the same time. A 4-node level whose first 2 nodes have 2 children each already reaches 6. So size it for the worst case, which is n, or let it grow. If QCAP is too small, the queue overflows and quietly overwrites live entries. So either size QCAP generously or use a growing queue, a linked queue, or a resizable array. This is where the level order space cost of big O of W comes from, on the complexity slide.